Hello, everybody. So today I will be discussing NASA exoplanets. My name is Shritha Gaddam, and a little bit about NASA exoplanets is that this method is one of the most powerful tools astronomers use to find planets beyond our solar system. So to start off, a little bit about me. So, um, I'm a senior at Decoy Creek High School, and I interned for NASA and George Mason University. And as a part of that internship, I researched exoplanet candidates, specifically exoplanet candidate test object of interest 3798.01. So I'm going to tell you a little bit about exoplanet research in general and a little bit about my research and how you can be a part of opportunities like that too. So to start off, the history of exoplanet detections first began in 1990. So a lot of the early methods were like radial velocity or direct imaging. And so radial velocity was pretty much where astronomers just measured how much a star like wobbled or moved. And obviously at that time, that was the only method available, but it wasn't necessarily the most effective method there is. So other approaches like direct imaging were also attempted, but it was challenging. As you can see, the picture right here was an attempt of direct imaging, yet it's really fuzzy and blurry because at the time the technology wasn't really ready for this. And since then, thousands of exoplanets have been found, and detection methods have become much more advanced. So this brings us into the NASA TESS mission, which TESS stands for Transiting Exoplanet Survey Satellite. This was launched in 2018, and its mission was to scan nearly the entire sky for nearby bright stars and look for planets that are orbiting them. So TESS is a successor to the Kepler mission, which was NASA's first big planet hunting mission. Yet the difference is that the TESS mission covers a wider field of view and is therefore more advanced. So the TESS mission uses the transit detection method within their scope to identify exoplanets. So to start off, the transit detection method works by watching for when a planet passes in front of a star. So as you can see right here, you're going to observe the star's light, and when there's a dip in the light for that star, you likely have a planet that's detected. So, by measuring how deep and how regular the dips are, astronomers can figure out whether that planet has a stable orbit and the specific size and type that that planet is. As you can see here, you can see the little light curve, and you can see that over time, you can see a tiny little dip. And of course, there's going to be a larger dip in stars that are smaller with a planet of the same size than a star that is larger. Because if you're using the same size planet, the little bit of light covering for a large star is different than that of a small star. So to move on, the transit detection method monitors monitors a star's brightness, as we previously mentioned. So this causes these tiny little dips in brightness. They're extremely small. As you can see, the scale on this graph is barely going up by like 0.02. So the dips are really small, but because our technology is so advanced, it allows for us to analyze these dips and see them. So by measuring how deep and how regular they are, we can really see the importance of this transit detection method and see how it works. So to start off, the very first step is to monitor a star's brightness over a long period of time. So usually one period can be changed from like a couple days to a couple months, and depending on the longevity and whether they think there is a planet or not, the method could be for significantly longer. The second step is to look for a periodic dip that suggests a planet is crossing, such as the dip shown in this light curve. And finally, the data is analyzed to confirm the planet's size, orbital period, and sometimes even its atmosphere. So, by being able to see the impact that the planet has in a specific light curve based on the star, you can really try and figure out a lot of details about that planet. And the main tool here is pretty much this light curve, which is basically a graph of brightness versus time. So the y-axis is going to be your time. The y-axis is going to be your normalized flux, which is the brightness, and the bottom is going to be your time. So for a real research example, I'm going to talk about my research that I did. So for me, I used test object of interest candidate 3798.01, and this candidate was extremely important and extremely different because for me, this data was never touched. So it remained untouched, and I was one of the first people to actually view it. So for myself, I came to the exoplanet conclusion that there is a chance that this exoplanet exists, but it's not fully confirmed. So when you're doing exoplanet research, two of the major softwares that you use are Astro J and Jupyter Notebook. So Astro J is a software platform where you can upload the pictures or the images of the star that you're taking, as you can see right here, and you can manipulate the data so that you can target your specific star, see the stars around it, and also understand if there's any significant impacts from those stars. Because a really important part of exoplanet detection, especially with the transit detection method, is that there's a very big chance of having false positives. So what these false positives are is that rather than the light curve being dipped due to a planet, it's dipped because of a nearby star. So as you can see here, T1 would be the star that I'm trying to observe, and then all the target stars around it could also potentially be a part of the light curve reducing its light at a specific time. Therefore, it's really important to understand that you can't always be fully you can't always be fully confident in the research that you have. And for Jupyter Notebook, it creates light curves such as the one I previously showed, like this one, and you just upload a specific file and it'll create a light curve for you over time. And one thing about these light curves is that each little dot is a different data point taken at that specific time and at that specific brightness. So to continue, here is my light curve that I created for test object of interest 3798.01. And if you look at this red right here, that's what the actual light curve is. And so you can kind of see that towards the end, you have this large dip, but in the predicted ingress time, which is the predicted beginning time of the transit, you're kind of missing data. Therefore, my data was mostly inconclusive, but because of this predicted egress time or the predicted ending time of the transit, it shows that there is a really good chance of an exoplanet being there. There just has to be more data. And that is a really big thing about collecting data and research in general, is that you do really need to understand that a lot of the data that you collect may not always be an answer that you want, and it may not always be a specifically defined answer that actually makes sense. So in this case, obviously, it was a little bit more inclusive, which was a little bit it was a little difficult sometimes to understand and develop that opinion, but with a little bit more data, we could really try and see if this exoplanet actually exists. So, what are the impacts and applications of this process? Well, TESS has discovered over thousands of potential exoplanets known as TOIs or test objects of interest. And so a lot of these planets and the planets detected have completely changed the way that we've studied our solar system. It really helps us understand what kind of planets exist and where they form. For example, within my research, the planet that I had was known to be a hot red Jupiter, and the star that I had was known to be a hot red Jupiter, and we can really see the different um, solar systems and exoplanets that exist outside of just our own, which is really important to help and find other worlds. Also, it's especially important for finding potentially habitable worlds that could host life, as I previously mentioned. So being able to find these new areas where life could potentially be created is amazing and would be a great development for the scientific community. But finally, the research also helps guide future missions, such as the James Webb Space Telescope, where it was released after the TESS mission, but it's kind of on the same idea as the transit detection method, except it's a little bit more advanced. So, in conclusion, um, the transit detection method as of today is one of the most successful detection methods there are, and TESS is a major contributor to this process. But the future of exoplanet discovery is looking extremely promising with newer telescopes that build on these foundations, especially with the James Webb Telescope, which is pictured right here, and beyond. So, if there are any questions, okay, so a couple of commonly asked questions about exoplanet detection, I can go over a few. So to start off, why is the transit method more successful than any other method? Well, to answer this, the transit method lets us detect thousands of planets all at once, so it's extremely efficient. But also, it gives key details for like planet size and orbital period, which other methods don't always provide, especially with the picture one or the radial velocity. It's hard to get those important details that the transit detection method gives us. And finally, when we can combine methods like the transit method with the radial velocity, it also allows us to estimate a planet's density and even more specific details, which is really important in trying to figure out whether life could possibly exist there. So, another question that is commonly asked is like, what's the process after you detect an exoplanet candidate? So, the candidate is labeled as a test object of interest or TOI, and then other telescopes, both on Earth and in space, perform follow-up observations to see if it's really a real planet. And then once that's confirmed, it's added to NASA's exoplanet archive. And so that is where I got my information from through my internship. They had special access towards that. And once you take it from the exoplanet archive, you can upload it into software such as Astro Image J, and you can understand and see whether that light curve, you can understand and analyze whether that light curve is really an exoplanet or maybe something potentially different. And then I can do like maybe like one or two more questions. So, another like really interesting question is how small of a planet can TESS detect? Well, TESS is a really sensitive, it's like sensitive enough to detect planets that are about the size of Earth, especially when they're around really small or nearby stars. It can't reliably detect planets that are like the size of Mars yet, just because the brightness dips are way too small for current technology. But obviously, with future missions, that can definitely be a real possibility. And so, like, on that note, we can also like talk about like what are the limitations of the transit detection method. Well, it really only works if the planet's orbit happens to line up with the line of our sight. So we do miss a lot of planets. And also, as I previously mentioned, it can give false positives, like when binary star systems transit a signal rather than a planet. So it's actually the star covering the light curve rather than the actual planet. And finally, this is also why astronomers also use follow-up methods like radial velocity or direct imaging to confirm so that we can really ensure that we're getting the most possible and most accurate information there is. So I think that's all that I have for today. Thank you so much for listening. And if there's any other questions, I would definitely like send them in and I would